let's look at section 5.2, convergence in measure, where we introduce a generalization of pointwise convergence of a sequence of functions to a limit function. And we'll see that many of the convergence theorems we've already encountered, they still hold if we'll replace pointwise, almost everywhere, pointwise convergence with this kind of convergence, this convergence in measure idea. So for our definition, take f sub n to be a sequence of measurable functions on set E, f a measurable function on set E. We're requiring that f and each of the f sub n's are finite almost everywhere on set E. Then we define the sequence f sub n converging in measure to limit function f if the following holds. For every eta greater than 0, if we consider the measure of the set of x values such that the absolute value of f sub n of x minus f of x is greater than eta, the distance from f sub n of x to f of x is greater than eta, if you like, the measure of that set approaches 0 as the index n given from the sequence of functions, the limit as n approaches infinity. So as n approaches infinity, we see the measure of the set on which f sub n and f, the limit function, are far apart, far being defined by parameter eta. The measure of that set of values goes to 0. Now, whenever we use a terminology, f sub n converges in measure to E on f, the measurability and the finite almost everywhere stuff up here, that's taken to be part of the definition of converges in measure. Royden gives a few more details on that on page 100, but convergence in measure implies, of course, measurable functions and implies this finite almost everywhere condition. Okay, first proposition says, suppose E has finite measure, let f sub n be a sequence of measurable functions that converges pointwise almost everywhere on E to f, and let f and each f sub n be finite almost everywhere, then f sub n approaches f in measure on set E. In other words, when E has finite measure, pointwise convergence implies convergence in measure, with the appropriate caveats about the finite almost everywhere. The finiteness of measure E, that's a necessary condition. If we drop that, we can find examples. One of the exercises deals with this. An example that violates this if we drop the finiteness of the measure of set E. But the big punchline here is, on sets of finite measure, pointwise convergence implies convergence in measure. So let's look at a proof of that. So we're getting a legitimate generalization of pointwise convergence in this convergence in measure. Okay. The limit function f itself is measurable. Pointwise limits almost everywhere. Pointwise limits of a sequence of measurable functions is measurable, as we've often seen. So we know the limit function itself is measurable. Let eta be greater than 0. So we're going to show the convergence in measure. Here's the arbitrary eta greater than 0. Let's also let epsilon be greater than 0, because we're going to borrow Egorof's theorem. Egorof's theorem said that, crudely put, pointwise convergence is nearly uniform convergence. So Egorof's theorem, which by the way required finiteness on the measure of this set, Egorof's theorem said there's a measurable set F, a subset of set E, with the measure of E set minus F little, less than that epsilon, such that we get uniform convergence on set F. We get uniform convergence off of this set of small measure, a nearly idea. So pointwise convergence, nearly uniform convergence. All right. Now, given the uniform convergence on set F, that means there exists a capital N, a natural number, such that when we take the index lowercase n greater than or equal to capital N, we have f sub n minus f in absolute value less than eta on set F. So for the uniform convergence on set F, we're taking the arbitrary positive number to be the eta that we started with upstairs. The given eta here. And that implies the existence of a sufficiently large capital N such that we get this kind of convergence uniformly on set F, throughout set F. So if lowercase n is greater than or equal to this capital N, then the set of x values where we get f sub n of x minus f of x greater than or equal to eta would be a subset of E set minus F. So we've got the inequality here holding on set F. So if we negate that and get a greater than or equal to, then that must happen off of set F. So we get that to occur on E set minus F. Quick little observation. This doesn't say greater than or equal to. This says strictly greater than. Still, we get the subset inclusion. We've taken something smaller than the set of x values we'd have where we get the greater than or equal to. So we still get the subset inclusion here. Now, we know E set minus F is less than epsilon in measure. That's how set F was chosen. So we know the measure of this subset of E set minus F, that is the x values in E, such that the absolute value is given is greater than eta. And that's what we're interested in when we talk convergence and measure. That's why we dropped a little or equals to part there. The measure of this set must be less than epsilon. So if we take a limit as n approaches infinity, this sequence of real numbers here, the measures of these sets must be 0. That is, we must have convergence in measure of f sub n to f. Little passing observation on this. To indicate this limit, I'd want to draw attention to, we let epsilon be greater than 0. We showed the existence of a capital N, and we've got the conclusion that when lowercase n is greater than or equal to capital N, the measure of this set is less than epsilon. And that's the very definition of limit of this sequence of numbers, which happen to be measures of sets, equals 0. Of course, we're dealing with non-negative, so I don't get absolute values on the measures of the sets. We're dealing with non-negative parameters when we deal with measures of sets. So we can make these sandwiched between 0 and epsilon by making n sufficiently large. And that's the very definition of the limit of a sequence of numbers equals 0. And that implies exactly what we wanted. That's the definition of convergence in measure of the sequence f sub n to function f. All right, so on finite sets, pointwise convergence implies convergence in measure. But even on sets of finite measure, the converse doesn't hold. So the following example shows that a sequence of functions may converge in measure, but not converge pointwise anywhere, in fact. So convergence in measure is a legitimate generalization of pointwise convergence. It maybe more cleanly relates to uniform convergence. So let's go through this. More precisely, convergence in measure is a generalization of uniform convergence on set E. If you got uniform convergence on set E, this set of x values, such that f sub n of x minus f of x is greater than eta, we make n sufficiently large, I can make this absolute value quantity less than eta by making n sufficiently large throughout a set on which we have uniform convergence. So this must be an empty set of x values when n is sufficiently large, sufficiently given in terms of the uniform convergence. So uniform convergence implies convergence in measure regardless of the measure of set E. All right, but let's look at it on a little finite measure set. The following is kind of cute. It's really easy to see if we look at pictures and graphs of these functions. So we're going to consider E to be the interval 0 to 1. We're going to cut it into n pieces, and we're going to do this for every natural number n, make the pieces of equal length in a specific way. So we're going to take the interval, cut it into one piece, the interval 0, 1, cut it into two pieces, the interval 0 to a half, and the interval a half to 1. then cut it into 3 pieces, 0 to 1/3, 1/3 to 2/3, 2/3 to 1, cut it into 4 pieces in a similar manner. And we're going to define f sub n to be the characteristic function on these intervals restricted to the interval 0, 1. So we keep everything happening on the interval 0, 1. And we're going to define the f function, which will be the limit in measure of this sequence of functions, to be identically the 0 function. First claim is we don't have pointwise convergence for any points in the interval 0, 1. And here's why. So let's look at the picture. What we've done is first, simply taken the characteristic function on the interval 0, 1. Second and third, so here's the partitioning the interval into 2 pieces. We've taken a characteristic function that gives us kind of a step up here and a step down here. Next, we'll take the characteristic function on this right-hand interval. So we get 0 and 1. Next, partition the interval into 3 pieces. From the first piece, we'll take on the value 1 and 0s on the rest. Second piece, value 1, 0 on the rest. Third piece, value 1, 0 on the rest. Do it again. Cut the interval 0, 1 into 4 pieces. We'll take a little step up here, 0 elsewhere. Click that step over to the second subinterval, third and fourth. Next, cut it into 5 pieces and do a similar type thing. Now we're getting convergence in measure because the limit function is 0, limit in measure is 0. And notice each of these little functions differ from the 0 function by an interval of length, I don't know, 1 over k or 1 over n. And n's going to approach infinity. So eventually, these functions differ from the 0 function only on a set of very small measure. And we can make that set as small a measure as you want. And that's what convergence in measure is about. Also, there's no pointwise convergence because pick a point, any point, along about here, the limit value is 0. But whatever point I choose, this point takes on the value 0 when plugged in the sequence of functions over and over and over and over, and then it takes on the value 1 when one of these little waves come by and hit that x value. And then it takes on the value 0 a bunch more. But a wave's going to come back and for this given x value, produce an output value from the function of 1. So every x value in the interval 0 to 1 takes on the value 1 infinitely many times because of the way these little waves, if you will, move across the interval. Well, then you don't have pointwise convergence to the 0 function. You don't have pointwise convergence to anything. These functions have subsequences that will converge pointwise, fix an x value, and we'll get a subsequence that converges to 0 or a subsequence that converges to 1 if you like. But this sequence of functions does not converge pointwise, but it does converge in measure. And that's what's argued here, slightly more quantitatively. We get the limit as n approaches infinity. The measure where f sub n of x and f of x and absolute value is greater than eta, that goes to 0. Provided eta is between 0 and 1, then the picture applies. If eta is greater than 1, we just get an empty set out. The result still applies. So convergence in measure, but not pointwise convergence. Okay, not that they aren't unrelated. Theorem 5.4 attributed to Riesz states, if f sub n converges to f in measure on set E, then there's a subsequence, denoted f sub n sub k, of the given sequence f sub n, that converges pointwise almost everywhere on E to f. And we just had some suggestive ideas that that was the case in the previous related to subsequences. Let's look at a proof of that. Okay, so we're looking for a pointwise convergence subsequence. Take k to be a natural number. We're looking to generate the function f sub n sub k here. Since f sub n approaches f in measure, then for all eta greater than 0, in particular for eta equals 1 over k. We know by the definition of convergence in measure, the limit as n approaches infinity of the measure of the set of x values where f sub n and f in absolute value is greater than eta, that is 1 over k. That limit is 0. So let's convert this limit property into an epsilon idea. So let's take epsilon to be 1 over 2 to the k. Knowing the limit of this sequence of numbers is 0 means I can make this sequence of numbers close to 0 with an epsilon of 0 by making the index sufficiently large. So here comes the n sub k. So we're going to take this limit equals 0. Epsilon is 1 over 2k. We know there exists a natural number. Let's denote it n sub k. Depends on the k because the epsilon depends on the k. So denote this n sub k such that for all values of the index greater than or equal to that natural number, traditionally denoted with a capital N, by the way, the measure of the set of x values is less than this epsilon value, this 1 over 2 to the k. Okay, so that's how we're going to choose the n sub k. Define e sub k to be that set of x values such that f sub n sub k of x minus f of x in absolute value is greater than 1 over k. All right, we know that this set of x values is less than 1 over 2 to the k. This holds for any j greater than or equal to n sub k, including j equals n sub k itself. So we get the measure of this set to be less than 1 over 2 to the k. Now, if we sum up from 1 to infinity, the measures of all those e sub k's, you're summing up this geometric series to get 1. Powers of a half will give us a sum of 1. So when we sum the measures of all those sets e sub k, we get something finite. We're going to throw the Borel-Cantelli lemma at this. I think this may be our only application of the Borel-Cantelli lemma. We talked about it. Let's run back and take a real quick look from section 2.5 at the Borel-Cantelli lemma. It said, if E sub k is a countable collection of measurable sets for which the sums of the measures of the E sub k's is finite, then almost all x belong to at most finitely many of the E sub k's. Almost all x belong to at least, almost all x belong to at most finitely many of the E sub k's. In other words, the x's that belong to infinitely many of the E sub k's, together they form a set of measure 0. So that's the almost all part. Okay, so the logic on this one is, the wording on this is a little tricky. So the Borel-Cantelli theorem tells us exactly that. Almost all of the x values lie in finitely many of the E sub k's. That is, for almost all of the x's in E, there's an index such that if we go beyond that index, x is not an E sub k. It's only in finitely many. There's a last one that this x value is in. Denote the index of that last one as, I guess, k sub x, capital K sub x, maybe -1 or whatever. We're getting the x values to not be in these E sub k's, provided the index is bigger than or equal to that k sub x. So if we go beyond the last one containing x, then we get this kind of behavior. Well, what's it mean to not be in E sub k? E sub k has this absolute value greater than 1 over k. So not being in E sub k and being in the domain of the function, being in set E, must mean that that absolute value is less than or equal to 1 over k. And this holds again for all k sufficiently large dependent on the x value. So for such an x, we must have, so we get this kind of behavior here, thinking in terms of a sequence of numbers now for fixed value for such x values. We've got the limit as k approaches infinity of f sub n sub k of x equals to f of x. We got pointwise convergence for these x values. So what's happening here is we chose k to be an arbitrary natural number, ultimately treating it like an epsilon value by looking at the 1 over k here. And we said if the index k is greater than or equal to some natural number, here we've denoted it k of x, all this is for a specific x value, that we get f sub n sub k of x minus f of x, an absolute value less than epsilon, as it were, less than the 1 over k. That's a definition of convergence of a sequence of numbers for a fixed x value. So we're getting pointwise convergence of these f sub n sub k's of x's for all such x's. That was almost all x's in set E. So this is holding for almost all x's. That's pointwise convergence almost everywhere. And we've got this subsequence, so determined f sub n sub k approaching f pointwise almost everywhere on set E as claimed. So convergence in measure doesn't let me access pointwise convergence directly, but in a sense, there's an indirect way to access pointwise convergence. Go to subsequences. I know subsequence exists where we get pointwise convergence almost everywhere. Okay, the next result's kind of similar to a couple of results we've seen before, except it involves convergence in measure instead of the almost everywhere pointwise convergence, and says, let f sub n be a sequence of non-negative integrable functions on set E. The limit as n approaches infinity of the integral over E of f sub n equals 0 if and only if f sub n approaches 0 in measure on E and f sub n is uniformly integrable and tight over E. We dealt with this in the setting of the Vitali convergence theorem, where set E had finite measure, and we didn't discuss the tight idea. We had replaced finite measure with uniformly integrable, and we required integrability of the functions, I think, in that stage. And in the generalized Vitali convergence theorem, we had taken as hypotheses uniformly integrable and tight together. And drawn this conclusion here. And that had replaced the condition of E having finite measure. I think it was. But this is similar to what we've encountered a couple of other times. Let's go through a proof of it. All right, if and only if, so we got two things to prove. First, suppose the limit as n approaches infinity of the integral over E of f sub n equals 0. We need to show f sub n converges to 0 in measure, and the sequence is uniformly integrable and tight over E. One of the corollaries we previously dealt with gives us the uniformly integrable and tight claim. Corollary 5.2 actually has a hypothesis of f sub n approaching x, f sub n of x approaching 0 almost everywhere. It's an if and only if result as well. This hypothesis is needed to draw a certain conclusion. We're using the logic in the other direction. We're assuming that conclusion and going in the other direction. We don't need this from Corollary 5.2. So Corollary 5.2 gives us a uniformly integrable and tight stuff. Now we just need to establish the convergence in measure stuff. So to show f sub n approaches 0 in measure on E, we're going to use Chebyshev's inequality. Relatively recently, hopefully you remember, it had a nice little picture associated with it. It's a parallel result in Calculus 1, the max-min integral theorem or something like that. Let eta be greater than 0. Chebyshev's inequality told us that for any natural number n, we get then the measure of x and E such that f sub n is greater than eta to be less than or equal to 1 over eta times the integral of f sub n. Chebyshev's inequality applied to f sub n. Only hypotheses there, I think, is that we have a non-negative function. That's what we were dealing with this. Possibly integrable was part of Chebyshev's. Possibly integrable was a part of it as well. I actually don't recall. But we get the measure of this set to be less than 1 over eta times this integral. Let's take limits as n approaches infinity of both sides. We're hypothesizing here that the right-hand side, these go to 0. By hypothesis, eta is fixed, so it must be as n approaches infinity. This has a limit of 0 as well. Everything's non-negative. The limit as n approaches infinity of the measure of that set must be less than or equal to 0. Of course, it's greater than or equal to 0 because it's a measure of a set. That is, the limit must equal 0, and that's the very definition of convergence in measure. So uniformly integrable and tight comes from a previous result, Corollary 5.2, and the convergence in measure comes from Chebyshev's inequality. So a lot of theory behind this stuff. Now we need to show the converse. F sub n converges to 0 in measure, and the sequence is uniformly integrable and tight, implies the limit of the integrals is the integral of the limits. The limit function is the 0 function. So suppose f sub n converges to 0 in measure, the limit function is a 0 function, and f sub n is uniformly integrable and tight over E. We want to show the limit of the integrals is 0. Assume it's not. We'll go by contradiction. Assume the limit as n approaches infinity of the integral over E of f sub n is not 0. All right, then there's some epsilon sub 0 and a subsequence f sub n sub k of the given sequence for which the integral over E of f sub n sub k is greater than or equal to epsilon sub 0 for all k a natural number. Otherwise, we can get the less than epsilon property out for all values of the index sufficiently large, and we would have convergence to 0. So negating the definition of the limit of a sequence of real numbers is not 0 produces this epsilon argument. You're staying away from 0 by this amount, epsilon sub 0, for some, right? Negating the definition is a little clunky, but it gives us this. All right. I really prefer to talk about pointwise convergence. And when we have convergence in measure, we can, for subsequence, that was the previous theorem, talk about a subsequence which converges pointwise. So the previous result, this Riesz theorem, Theorem 5.4, tells us that some subsequence f sub n sub k sub j of f sub n sub k, so we're at a second level of subsequences here, this must converge to the limit function 0 pointwise almost everywhere on E. Right, because the sequence f sub n sub k converges in measure. Yeah, we had f sub n converging in measure, so this subsequence converges in measure. So this subsequence contains a subsequence, which must converge pointwise almost everywhere, Theorem 5.4. Now about this subsequence, it converges pointwise almost everywhere to the 0 function. I would expect the limit of that particular subsequence, limit as j approaches infinity of the integral, to equal the integral of the limit. We got a theorem to justify that? We do. We get the generalized Vitali convergence theorem. Vitali convergence theorem requires finiteness in measure. We don't have that. The generalized Vitali convergence theorem doesn't, but it requires uniformly integrable and tight. This subsequence, it's uniformly integrable. Yeah, subsequences of uniformly integrable sequences are themselves uniformly integrable, and same with the property of tightness. Both of these required, if sets were sufficiently small, then we had certain types of behaviors throughout that family of sets, certain types of behaviors of the integrals related to those small sets. Well, if the whole family satisfies it, then some subfamily also satisfies that condition. So the subsequences inherit the uniform integrability and the tightness, in other words. So we can apply generalized Vitali convergence theorem to the subsequence. It's uniformly integrable, it's tight, and it converges pointwise almost everywhere. Then the limit of the integrals is the integral of the limit, this time with a sub index, the j approaching infinity. But this can't be the case because this contradicts what we had up here. We're taking a subsequence of this collection here, and we're claiming up here that the integral over e of these things is greater than or equal to epsilon sub 0, provided k is sufficiently large. Well, this includes a bunch of those k's sufficiently large. Well, we can't have these going to 0 and have the thing bounded away from 0 in that sense. So there's the contradiction. The assumption we made that the limit as n approaches infinity of the integrals is non-zero must be false, and the integrals have a limit of 0 as claimed. So there's the converse. And another result in the same vein as those previous ones we've seen. And I've actually an exercise in the book, problem 5.8, really gives a motivation for this convergence in measure. We know it's a generalization of pointwise convergence on sets of finite measure at least. And in this exercise, you're to show that Fatu's lemma, the monotone convergence theorem, the Lebesgue dominating convergence theorem, and the Vitali convergence theorem, all these things hold provided you replace pointwise convergence almost everywhere with convergence in measure. And we see convergence in measure is a weaker condition, since pointwise convergence on sets of finite measure at least implies convergence in measure, or maybe more specifically, uniform convergence is going to apply convergence in measure. But we could redo all of those old convergence theorems and express hypotheses in terms of convergence in measure instead of pointwise convergence. So there's your 4 more giant convergence theorems, if you like. I'm happy leaving real analysis 1 with a thought that all those monotone convergence theorems, they deal with pointwise convergence. They can be slightly generalized and stated in terms of convergence in measure as well. But in your memory banks, probably carry around a thought of pointwise convergence, because that's certainly more common, though it can be generalized. And that takes care of section 5.2. One more section will complete chapter 5, and the last section deals with some necessary and sufficient conditions for a function to be Lebesgue integrable in a certain sense concerning bounded functions. More of that in the next section. I'll see you there soon. Have a nice day.